We have success anymore. Off we go. All right, ladies and gentlemen. Candy, can you see through this? Okay. I will move it. I'll just put it right down here. It's a Holy arrangement for physics. We're doing mechanical advantage of machines. All right, so next unit is on bonding. And critical to the idea about bonding is the trends we were talking about before. At the core of those trends is the relationship between the effective nuclear charge that's pulling the electrons in, and then all the electrons in their cloud repelling each other. Now, if you paid attention to the corny video at the atom disco, this will make a lot of sense, and I'm going to refer back to that. And I actually color-coded them that way too. The reason that atoms bond, the whole reason they bond, is so they can attain a lowest energy state. The whole reason that atoms bond is so they can attain a low energy state. And the way they do that, the best way to do that, is to look like a noble gas, to be isoelectric with a noble gas. So if you're oxygen and you've got 6 electrons in your outer shell, 6 valence electrons, you want to get 2 more. And then you'll be isoelectric with neon. If you're fluorine, you have 7 valence electrons, you want to be isoelectric with neon too, so you're going to get 1 more. That's going to drive your potential energy down. Atoms bond to get to the lowest potential energy. They start at a high potential energy that we just arbitrarily make 0. And then they come down to a low potential energy. And there's 3 ways they do that in this class. The first way is forming an ionic bond, like in the video, when chlorine took sodium's outer electron. In an ionic bond, electrons are just taken. The metal, which doesn't hold its electrons very strongly, gives up an electron. The non-metal, which has a very high effective nuclear charge, takes the electron, like sodium and chlorine. The second way is a covalent bond. In a covalent bond, electrons are shared. We spend a lot of time in covalent bonds in this unit. And here's how it works. I might not have another. Oh well. Let's pretend this is a tennis ball. Okay. This oxygen says, "Hey, oxygen, I need 2 more electrons." "Hey, other oxygen, I also need 2 more electrons. I have an idea. Why don't you give me 2 electrons, and then I'll give you 2 electrons? Won't that mean that I have 4 sometimes and you have 8? No, because the electrons will travel between us at the speed of light, so it will appear that we both have 8 all the time." That's how covalent bonding works. So 2 atoms share electrons. They always share pairs of electrons. And because they are both giving and taking that electron at effectually the speed of light, it appears that there are more electrons than there actually are. So oxygen with 6 gives 2 to the other oxygen. It doesn't then have 4 because the other oxygen is giving 2 to it, so it appears that both of them have 8 electrons. They are sharing electrons. But it's a sharing electron that happens so fast that neither atom misses their electrons. Does that kind of make sense a little bit? We're going to develop it as we go. And then the 4th type, we've actually talked about metallic bonding. The 4th type of bonding happens in D block metals, where the electron orbitals, those really long d orbitals, those d orbitals overlap and create a 3-dimensional web of electron clouds. So electrons go from one atom to the next atom to the next atom, and we call that the electron C model, where all the electrons are shared. So after we talk about bonding types today, we have a few really fun labs. We're going to use these toys. These toys right here. Let's put these guys here. I got back when the school had money, I got Amy to give us a whole bunch of these model sets. They're really great. So after we talk about bonding types, then we're going to talk about the intermolecular forces that exist between atoms. Then we're going to talk about how atoms arrange themselves in real space. Yes?
So metallic bonds, it only happens for the elements in D block?
Yes. I mean, in reality, once you get down below 4D, it also happens for the atoms that have D block electrons. But for this class, just assume it's just the D block metals.
And then the covalent and ionic bonds could be any of them?
Covalent bonds will always be two nonmetals, two or more nonmetals. Actually, everything in this class is binary. Two nonmetals. I need more water. The ionic bonds are always going to be between a metal and a nonmetal. And kind of like the video where sodium went to disco and had that outer electron. They're like, "You're going to lose it tonight." And then chlorine came along and stole that outer electron. Chlorine was the nonmetal. Sodium was the metal. Because sodium's effective nuclear charge is so small in comparison to chlorine, chlorine just like ninjas the electron right away. All right. Any other questions? Yes.
So in the D block, if like everyone's supposed to have 8 electrons in their outer shell, how does that work with the D block? There's like 10 of them dead.
Okay, good question. The D block electrons are never in the outer shell because you know how it goes 4s, then 3d, then 4p?
Yeah.
So it is the 4th level that those 3d electrons find themselves in. So they're never in the highest shell.
Okay.
So, and we move down 1, it's 4d. Well, the 4d is stuck between the 5s and the 5p. So the d electrons are always 1 level below the shell, the highest shell. So you never have to be worried about it. All right. More questions, Seamus, or are you just doing?
No, I'm taking my hoodie off.
Okay. I know it is. Actually, I think they turn the heat on here. Of course, it also just be we have 3 outside block walls. Okay. If you're ready to move forward, give me a thumbs up. You have any more questions? Wave them around. All right. Let's get right into it. Here we go. Okay. So, quick review. Very quick review. Remember, an ion is an element that has gained or lost electrons. If it has lost an electron, we call it a cation. If it has gained an electron, we call it an anion. And we also remember that cations are always bigger, are always smaller than their neutral atom, and anions are always bigger. The octet rule tells us that all atoms want 8 or 0 electrons in their outer shell. Another way to think of this is all atoms want to be isoelectronic with the noble gases. Kind of like chlorine again. You all have such beautiful outer shells. How do I get one like yours? Yeah, okay. So metals and nonmetals. So if you have chlorine, again, chlorine has a very high effective nuclear charge. It seeks to gain an electron to become a chlorine ion. That is its low energy state. Sodium, on the other hand, it's kind of a misnomer to say it wants to lose 1 electron. It really just doesn't hold on to that electron very closely. It doesn't necessarily want to lose it, but it loses it very, very easily. And then you have these positively and negatively charged ions, which then stick together. They are electrostatically attracted to each other. So you make the ion by pulling the electron from one metal to the nonmetal, then they stick. That's ionic bonding. Yeah.
The cations are the gain, right? When you gain one.
No.
Cations
So
are lost.
cations are positive. Think like the T has a cross in it. Cations are positive.
So they lose. They lose.
They lose electrons. Yeah. And then anions are what you get when you make a negative ion. I like to think negative ion. Negative ion is an anion. I don't have one for cat other than the positive. Yeah, but cats aren't really positive. They're just kind of.
They're like emo dogs.
They're worse.
Yeah.
Anyway, if you have a cat, you know what I'm talking about. Oh, it expressed its gratitude for me to feed it by peeing on my laundry. Anyway, moving on. Okay, so let's move on.
Share.
This is kind of fun. Sodium chloride. Yeah. We talked, like, one of the very first things we talked about is how compounds tend to not be anything like their ions that make them up. Okay. So, ionic bonding, you get a bunch of ions together. Positive ions are attracted to negative ions, kind of like my model over here. In 3 dimensions, this is a 2-dimensional model. Notice how it's alternating positive, negative, positive, negative, positive, negative. In 3 dimensions, they form what's called a crystal lattice. That is the 3-dimensional arrangement of ions, a crystal lattice. And one of the really cool things about salt crystals, one of these days I'm going to grow some pretty cool salt crystals, is if you look at a salt crystal with the naked eye, it's a cube. The next time you have salt looking at a salt crystal. So next time you have some salt, look at a salt crystal really up close, it's a cube. In fact, if you were to zoom in on it with a microscope, it's still a cube. And if you were to crush it into a powder and then zoom in really far at the molecular level, it's always going to be a cube because the crystal lattice for sodium chloride is that alternating positive, negative, positive, negative. It has to make a cube. Oh, don't want to talk about dissolving yet. The formula unit is the reduced form of the lattice. It is what makes up the lattice. So the formula unit for a salt crystal is simply 1 sodium and 1 chlorine. That's the formula unit. Every crystal or mineral has a different formula unit. Okay, I'm going to plant a seed and talk about intermolecular forces a tiny bit. Intermolecular force is what holds molecules together, different molecules together. So when water dissolves something, it does so by surrounding the ions with water molecules. I'm going to kind of jump around a little bit because it's impossible to talk about dissolving without talking about intermolecular forces and what we're going to be talking about in polarity. So this is my water molecule. I'm going to draw it really big. I've got an oxygen. Woo. And that oxygen is connected to 2 hydrogens. So far, so good? Now we're going to talk about something called polarity. But for now, just realize that this molecule has a, let's make it a negative end and a positive end. Just like a magnet has a north end and a south end, molecules can have poles. They can have north ends and south ends. Well, what happens, you'll notice here, what do you notice about all the water molecules around the green chlorines?
They're green. They stick to the grape. They stick to the white ones.
Yeah. The negative chlorine ion gets surrounded with the positive end of the water. And notice the positive sodium. The positive sodium gets surrounded with the negative end of the water.
Kind of like opposites.
Exactly. So this is how water dissolves things. So when you put your salt in the water and stir it around, because you got a sore throat, you're going to gargle some salt water. The water molecules come in. The positive end of the water molecules are going to latch on to the negative chlorine. And the negative end of the water molecules are going to latch on to the positive sodium. Kind of like this, like I've had on the board since the beginning of the school year. An electrolyte is a solution that conducts electricity. An electrolyte is a solution that conducts electricity.
That's not right. We're not bad.
We have a whole subunit on electrolytes. We have a whole subunit of electrolytes next spring.
For my okay.
All right. So an electrolyte is a solution that conducts electricity, and it conducts electricity because ions move through the solution. Spend more time on that later. Okay. Any questions about this whole ionic stuff?
No.
Metallic bonding, we talked about this before. Metallic bonding happens when the d block orbitals overlap really well, and by overlapping, they cause the electron clouds basically are like a giant three-dimensional web. And the word we use for that is delocalized, meaning if you're copper atom 1 and I'm copper atom 2, neither of us really know where our electrons are. We're just sharing our electrons, kind of like the air in this room. We're all sharing the air in this room. You're like, no, this is my air. Sorry, no. The air that I'm breathing out, you're all breathing in to some extent. So again, we talked about this before when we did the individual groups last unit. This is what gives D block metals their particular properties. They are extremely shiny because those electrons can move around and absorb and re-emit any light they want. They're malleable. You can take, just like I can move you guys around, like, hey, Tate, go in the corner of the room. He's like, but there's no air over there. Yeah, there is, because we all share the air. Okay. There's no well, there's no air over there. But when we move the protons around, we move the nuclei around, the electrons just flow wherever we move them to. Ductility, once again, we can form into wires. Really good at conducting electricity because we can just move electrons from one to the other. And then they also conduct heat because the metals vibrate very well. That's really what heat is, just vibrating things. All right. How are we doing? If you have any questions at this point, wave your hand around. Otherwise, give me a thumbs up. We're saying we're ready to move forward. Okay. Let's talk about the good stuff. Let's talk about the covalent bonding. So covalent, also called molecular bonding, is what happens when you share electrons. Like my little oxygen atoms before. They share electrons. Some electrons, or some atoms, want one electron, so they're going to share one to get one. Some want two, so they're going to share two to get two. Some want three, so they're going to share three to get three. But ultimately, electrons are always shared in pairs. Each species in the bond shares the same number of electrons as the other species in the bond. So you get shared electron pairs. This is why the diatomic molecules are the way they are. The 7 diatomic molecules occur because they share electrons with other species that are the same as them. So bromine has 7 valence electrons. It needs one more. So bromine A shares an electron with bromine B. So by sharing that one electron with bromine B, bromine A has 8 electrons. But bromine B also has 8 electrons. And because it happens at the speed of light, they don't miss their electrons. Is that clear? Like we were talking about before?
Yeah.
Yes.
So it's kind of like you go together and you buy a video game. And you're like, okay, half the time the video game is going to be at your house. And half the time video game is going to be at my house. And then imagine it keeps going back faster and faster and faster between you that neither of you miss it. That's what's going on in your covalent bond. Now, sometimes it's not just one electron that gets swapped. Oxygen shares 2. And nitrogen, Find nitrogen on the periodic table. How many valence electrons does nitrogen have? 5. So how many valence electrons does nitrogen need? 3. So how many valence electrons does each nitrogen share? 3. Nitrogen makes a triple bond. All right. How are we doing with this? Okay, give me a thumbs up if you're with me. Okay, if you have any questions, wave your hand around. So, to summarize, question.
Does it only happen in that top row?
No, it only happens in the nonmetals. So when you go aluminum, silicon, germanic arc down here, you don't do that. You only do covalent bonding in this kind of triangle from carbon, phosphorus, selenium, iodine up to fluorine. So imagine that triangle right there.
Okay.
That's where you do the covalent bonding, and hydrogen up there over there too. Good question. So in summary, if you want a number of electrons, you share that number of electrons. But because you give it and take it at the speed of light, it's not like you miss it. It's more like you have an extra electron. Moving on. Okay. Hey, you're a band. And a volunteer. Perfect. All you use rubber band for this
If you
experiment.
don't want to do it, Seth, I'll do it.
I'm good.
Oh, you both want to do it?
I'll do it.
Okay. You can have one. Seamus, is that you?
Yes.
Okay, Seamus, you can do it too. Oh, there it goes. Way over there.
Take that feet.
Okay.
I do.
I thought you were a receiver. So
All right, Seamus and Seth. Without hurting yourself, stretch the bond the bond as far as it can go. Okay. So what you're seeing is a single bond. There's 2 pieces of rubber between, representing each atom. So their hands are their atoms. Okay. Each atom is donating a single electron. How many electrons are in the bond?
1.
2, because each atom donates an electron. Okay, now double it. So you know, like you fold over the rubber band. Okay, so now each atom donates how many electrons? 2. So there's a total of how many electrons in the bond? 4. That's a double bond. And you might notice they didn't stretch it as far. And they probably have to exert a little more energy. So a double bond is a stronger bond, but it's also a shorter bond. I'll say that again. A double bond requires 4 electrons. It's a stronger bond and a shorter bond. Now, if you can make it like a triple without making it a quadruple, give that a try. I'm not going to wait for you. But imagine if they did a triple, kind of like you do thirds and flip it over on thirds. If you did a triple bond, would it be even shorter?
Yes.
Yeah. Would it be even stronger?
Yes.
Yeah. So we have multiple bonds. The more bonds you have in between the same atoms, the stronger it's going to be and the shorter it's going to be.
So more bonds equals stronger.
More electrons in the bond. So a triple bond is still 1 bond, a double bond is still 1 bond, but there's more electrons in the bond. And the more electrons in the bond, the stronger the bond's going to be.
In bonds equals stronger equals shorter.
Now he's got it.
Boom.
Yeah. And in case you were wondering, there are no quadruple bonds.
Why
Why
not?
not?
The geometry doesn't work. So if you take AP, we'll actually learn how the geometry of bonds works, and we'll learn that you can't have a quadruple bond because it's kind of like holding something in front of you and behind you very, very heavy. So you can hold something in front of you that's very, very heavy, but you also can't hold something behind you because both of your arms are forward.
John could do that. He benches 225.
Maybe he can create the 4th bond. Okay, now this is what I alluded to at the beginning of class. When atoms bond, they do so to get the lowest energy possible, what we call the lowest chemical potential energy. This is a really great graph. It's from if we use your textbook, this came from the textbook you would use. And I have never found a better one. When atoms are separate, they're at a 0 energy state. When they bond, they attain a low or negative potential energy state.
Bye, Miss Igo.
Bye, Miss Igo.
So in this case, you got a single bond, two hydrogen atoms in this case. When the hydrogen atoms are separate, they're at a zero potential energy. When they bond, they attain a negative potential energy. If we want to break the bond, we have to put energy into it to break it. Kind of like with Seth and Seamus from Rands, if they're going to break that bond apart, they have to apply a lot of energy to snap it.
I don't think Seamus is strong enough.
Join is
It's like it's going to go right at
That's all you got?
Join
I was 225.
well, there we go. So the
No.
so when if you have something that's bonded, it's going to have a negative potential energy.
Yeah, I'm ready.
To unbond it, to break the bond, we have to apply energy to get it back to zero. Because a zero energy state is high energy. I know, it's just they basically had to have a 0 point. So they basically said zero energy means unbonded atoms all by themselves. When you bond, you bring them into a low potential energy state. If you break the bond, then you have to put energy in to get them back up to a zero energy state, which is a high energy. You guys realize that zero is more than negative 436?
Yes.
Yeah, no, I learned that in math.
Good.
What is 75?
Distance.
Oh.
The PM is the picometer, which is 10 to the negative 12. It is literally the distance between the nuclei. And that's going to come into play next week when we talk about bond distances. Yeah.
Wait, so atoms that are like the most stable have the lowest potential energy?
Yes. In fact, if you are taking notes, make this diagram.
Okay.
Is it a hard diagram?
No, not at all. So you got an axis, you got distance on the x-axis, and you got energy on the y-axis, and it goes, and then this is zero. It's zero. This is a test question, by the way.
Oh, yes, okay.
A. E, wait, what's the bond?
This is a test question that everybody's going to get. It's not even a random one.
Where's the D?
Distance.
Oh, it's
Distance and energy.
Let me guess, it's going to do periodic.
And that's zero. No, not at all. So this is the energy graph for a single bond.
Is that little O there 0?
Yes.
Okay.
Zero.
That doesn't help. Let's try zero. Zero. And this is a single bond. And let's just arbitrarily make it negative. I'll make it negative 100. Single bond. Make it negative 100.
Single bond, negative 100.
That's a lot of negatives.
It's a lot of negative energy.
Negative.
What this means is if I want to break this bond, it's going to require 100 units of energy. What I would like you to do is this. With a dashed line, show me where a double bond would be. What would the graph for a double bond look like?
Would it be more than
This is a test question.
negative 200?
Not necessarily. It's not. Bond numbers aren't. They're not additive. But sketch a graph. The numbers are not important. Just sketch the general shape of the graph.
It'd be.
Wait, no.
There's another
I'm
bond.
actually about to crash out. I put that.
The W is a detractor on the quiz.
What?
The W is a detractor on the quiz.
Was there?
That means the wrong answer.
Oh, detractor, so like,
Oh,
detractor.
A detractor on a test is a question
Would it
that
just
is
be
designed to
deeper?
No, actually stop. No,
throw you
actually
off.
stop.
Yeah.
I'm not even kidding.
Why
Would it
not
just be
call it
steeper?
like dig?
I'm not even. I'm not kidding.
Yeah.
You see, I'm kidding. Look at my face. Look at my face. Am I kidding or not? Okay. I'm not kidding. Not really.
Okay. All right. A double bond is a stronger bond. Are you paying attention?
Guys.
The double bond is a stronger bond. So where should the bottom of the curve be? Higher or lower?
Higher.
Lower. Come on.
Lower.
Why?
Because it's going to have a lower potential energy. It's going to require more energy to bring it back to zero. So it's going to be somewhere down here.
Wait, would this be right?
No.
Like that? That's like the negative 100 line, and then like that's the 0 line. And like that's-
Wait, would it be?
Okay, I can't. You haven't actually drawn anything yet. Okay, so for the amount of energy,
Would it be double?
not necessarily.
No.
So it's not. So it's.
You said it's
We're
not
having a conversation. Yeah, it's not additive. It's like a double bond doesn't have twice as much energy as a single bond, but it does have more. Okay, so a double bond in the y-axis is going to fall below the single bond. Where is it going to be on the x-axis? Is it going to be to the left, or to the right?
To the right. Left.
It's going to be left. It's going to be a smaller bond. So the bottom is going to be more like that.
That's what I did.
That's what he did.
Good job, bro.
So a double bond is going to have a lower potential energy, require more energy to break it, and it's a shorter bond, so it's going to be closer to a zero. It's going to be a shorter distance. All right. Anything else to talk about? Let's see. Yep, sure do. All right, cool. If this resonates with you, give me a thumbs up. If you need me to go over it again, wave your hand around.
No.
How does a double bond have lower potential energy?
The easiest answer to say is it requires more energy to break because you have to move more electrons back to their shells. That's probably the best thing at this point.
So it goes not as deep, or does it go deeper?
A double bond goes deeper.
And then just closer to the
Yeah,
y.
it's a double bond would be more negative and shorter.
So it has lower potential energy and it's lower distance.
Yeah, and we say lower potential energy, we mean more negative. Again, this is on the internet. This is one of those things that a lot of teachers teach wrong. A lot of chemistry teachers will say bonds hold energy. And when you break the bond, it releases energy. The exact opposite is the case. Bonds don't hold energy. They are at a low energy state. In order to break the bond, you have to put energy in to bring it up to zero. Yeah, I know. I do teach teachers sometimes. But you'd be surprised how many. You guys don't realize it because I'm your teacher, but you don't realize it because you'll encounter people in college who will think that because that's the way they're taught.
So when they break, they don't release energy.
Correct. To break, you need to put energy in.
That's beautiful.
It's not like a firecracker. You're like, oh, a firecracker explodes and sends energy everywhere. It's the opposite of that.
Like how Seamus needed to use all of his might to try to break.
Precisely.
No, it was actually
Doesn't mention 25.
Okay. The most important periodic trend we talked about last time was electronegativity.
Yes.
Electronegativity is the strength of an atom's ability to bully electrons from other atoms. Remember the model, the little analogy I told you about? Like you go together and you buy a video game. Now the analogy is falling apart because you guys don't buy video games with like physical means anymore. But back in the day, we had cartridges and we had discs. So imagine you're me when I was 8. I'd be like, I need to buy a game. I need to buy Zelda. It's $60. I only have $30. So it's like, okay, you give me 30, you give me 30. We'll put it together. We'll buy it together. And then on half the days, you have it. Half the days, I'll have it. Well, that's how bonds work too.
Or you guys just buy two.
But if one person puts in more, like 40, the person puts in 20, then the game should spend more time with that person. Well, the electronegativity works that way. If you have two atoms that are sharing electrons, but sharing them unevenly, you have a polar covalent bond. Literally, a bond that has a positive and negative pole. And this pole is called a dipole. If you've never heard the word dipole before, it's anytime you hear a north pole or a south pole, that's called a monopole. The two poles together are a dipole. Di means
Two.
Two. Like you ride your dicycle around.
Yep.
My bicycle.
Oh, well, we want to call it a bipole, but they called it dipole instead. So let me show you an example of a bond that is polar. This oxygen-hydrogen bond and that oxygen-hydrogen bond are polar because oxygen is more electronegative than hydrogen. And if you were to look at the bond, so here's the oxygen, here's the hydrogen, and you were to look at the electron traveling around the hydrogen and the oxygen, it's gonna, or two electrons, there's actually two of them, remember there are two, they have to move in a pair in opposite directions. So those electron pairs of the bond spend more time around oxygen because oxygen is more electronegative. By quite a bit, in fact. If I was drawing this by proportion, it'd be like oxygen would be like here and hydrogen would be like here. Okay, so what we do is we show this bond with a dipole. Are you ready? Pay attention.
Okay.
A dipole is an arrow that goes along the bond. The arrow, oops, backwards. The arrow points from an area of positiveness to an area of negativeness. The positiveness gives you a little plus there, and the negativeness. And to show that there are positivenesses and negativenesses, we use this letter. It's a sigma. Imagine making.
Sorry.
Yeah, people are always messing around with Greek letters. Sigma, whatever. Anyway, here we go. To make a sigma, you go S with a little loop on the back. This means partial. Are you paying attention?
Yes, I am.
This means partial.
That's sigma.
So that's sigma. It's, to make a sigma, you make an S with a little loop on the back.
To make sigma, you have to channel.
Whatever. Anyway, so this side is partially positive, so we make a little sigma with a positive sign. This side is partially negative, so we make a little sigma with a negative sign. And we do the same thing with the other bond. Partial positive, partial negative. So bonds between atoms that are not the same will be polar bonds. The atom that is more electronegative will be the partially negative side, and the atom that is not more negative, it is less electronegative, will be partially positive. Comprende?
So for the
Yes.
oxygen hydrogen graph, it'd be going.
So this for this one right here?
Yeah.
Yeah, this would look like this.
Okay, that's what
Because the hydrogen is less electronegative, so that's where we get the partial positive. The oxygen is more electronegative, that's where we get the partial negative. Again, this is called a dipole. Sometimes it's called a bond dipole. Now, if they are the same, they have the same pole, then you get what's called a nonpolar bond. A nonpolar covalent bond is what you get when both atoms have the same pole for their electron pair. We are almost done. Okay. We've talked about a lot of stuff.
Yeah.
There's one concept left. The water molecule is polar. The whole molecule is polar. That allows it to attack the positive negative crystal. The reason the water molecule is polar is because those two bonds don't cancel out. If they cancel out, like if the bonds were like this or like this, then it would make a nonpolar molecule. So we have polar bonds. We add the bonds together to determine if the molecule is polar. Okay. It's called vector addition. Remember number lines in elementary school?
Yeah.
You like +8 and -4.
Yeah.
Well, that would be like a lopsided, so it'd be +4. Well, if you had a +8 and a -8, they end up at 0.
Yeah.
Well, if your bond dipoles cancel out, you have a nonpolar molecule. If your bond dipoles do not cancel out, you have a polar molecule. And that's what goes on in water. So in water, you have two bond dipoles that sum to create a molecular dipole. And a molecular dipole you draw outside the molecule. Get rid of all the extra stuff here. So if I want to draw the molecular dipole, I would draw it in the proper direction, but outside the molecule. And I would give this side a partially positive, and this side a partially negative. Which is why the sodium is attracted to the negative side, and the chlorine attracted to the positive side. So how do you know if something's going to cancel out? If it's asymmetrical, then it's impossible for the bonds to cancel out. You know what asymmetrical means, right?
Same on both sides.
That's symmetrical, and
Asymmetrical.
asymmetrical
All
means
around.
different. Yeah, not the same on both
Oh,
sides.
Oh,
So if you have an asymmetrical molecule, it is going to be a polar molecule. It has to. If you have a symmetrical molecule, it will most likely be a nonpolar molecule. Most likely. I've tried to shield you from exceptions. I'm probably going to fail, but I've tried to shield you from exceptions. So this is an example, carbon dioxide. This is an example of two bonds that are polar. Oxygen, carbon, carbon, oxygen. Two bonds that are polar that push away from each other and cancel each other out. So two molecules with polar bonds, or a molecule with two polar bonds that cancel each other out to produce a nonpolar molecule. And that is a test question. Which of these molecules, A, B, C, D, E, which of these molecules have polar bonds, but the molecule is nonpolar? You're gonna figure it. You're gonna find out how that is in this, once you actually work with this unit. All right, last thing. Here's anything else in a second. Like dissolves like. What it means is polar molecules behave well with other polar molecules. Non-polar molecules behave well with non-polar molecules. But non-polar molecules do not behave well with polar molecules.
They go boom.
Well, the go boom from the video was because you had the difluoroethene, which is super polar. And you add it to water, which is super polar. So they agree so well, they throw a little party. And they drop so far into the negative that the amount of energy they release when they make a bond causes an explosion. If you didn't watch the video, you don't know what I'm talking about. If you did watch the video, you know what I'm talking about. The reason there was an explosion is because they went from 0 to way negative. In order to go from 0 to way negative, you have to give off energy. And they gave off a lot of energy. Now, that did not happen when he put the difluoroethene in the water, in oil. Because oil is non-polar. It wasn't going to mix with the oil. So it didn't explode. Get the idea? Polar things react with polar things, or interact with polar things. Non-polar interact with non-polar. If water is polar, what is butter?
non-polar.
Non-polar. You know this because you ever get butter on your hands, have fun. You need to use soaps and stuff to get it off. Because water is polar, butter is non-polar. They don't agree with each other. Like toast. Okay. Questions? All right, cool, I'm done.
Oh, really?
Yeah, we're done. Sorry that went the whole period, but it's pretty important.